Excellent. Should now be recording. Hopefully I have a strong signal down here. Am I being heard on for those of you who are hybrid? Can you hear me fine? Am I coming through at a reasonable bandwidth? Hope so. Let's see. Perfect. Okay, so for today's lecture, I want to continue our venture down the C programming language, mapping what we know from Java on top of C. And this, once we're done like this tour, I'll go ahead and assign the very first lab, which is going to have you do some basic programming in C. But before we do that, I kind of just want to give a overview of everything. So today's class, we're going to pick up where we last left off. So we last left off with operators, right? And so it makes sense then that we can start talking about control structures. So in order to go ahead and run multiple or connect multiple statements together, we use curly braces, very similar to Java. Java got its metaphor of being able to create a block of code where there's a shared scope in that block through curly braces. And so when we go to create any control structure or any kinds of joining of statements together, we'll default to curly braces for the same rationale. And so I don't know how hard this was articulated, but this might backfill some of your knowledges. When we talk about things like selection statements, repetition statements, you can, by default, use one of those without any curly braces, right? But it only affects that one statement that immediately follows it. And so the value that a curly brace brings is it allows you to take multiple statements and combine them together so that our compiler will execute them as an atomic entity. So whether you had realized it was a way of compounding statements together or not, I'm going to just go ahead and define that. Okay, so with that said, curly braces, open, close, exactly like in Java. I don't even have code to demo that. Okay, so now let's go to the actual control structures. Well, let's see here. My Finder is not looking great. So let's see here if I can go ahead and what am I using? This is Visual Studio. Let's see here. Let's clear this. So I attempt to kill Finder, see if I can get it working or not. Will that wreck my system? The gamble. Okay. Let's see what happens if we force quit it. Okay. Now let's see here. There we go. Okay, now, perfect. And let's change this view to be based off of list view. Perfect. Okay, so let's take a look at our selection statements. So selection statements is the generic term for our single selection, our double selection, and our multi-selection statements. You probably know them more as if else, or nested if statements. So we'll take a quick gander at the code here. I'm going to, of course, include, so I have this preprocessor directive that's going to include my standard input-output header. So I get access to my print function. I'm going to have this main function, returns an int. We're going to return 0 at the very end of our function call if it returns normal. Okay, so now let's take a look at single selection. Single selection, well, first let's create a local variable locally scoped to our main function. We'll just call it number. We'll assign it to 15. This is initialization. We've seen this before. Okay, single selection looks exactly like we would expect in Java, right? If is the keyword we use. We use a set of parentheses that we evaluate a Boolean-based logic, right? So something that will effectively be 0 or non-zero. If it's 0, that represents a false value. If it's any non-zero value, it represents a true value. And so if this were a non-zero value, then we would go ahead and print number is greater than 10. Then double selection, we can partner an else to our if statement. So single selection is really a decision point. Do I execute this block of code or this statement or not? A double selection is guaranteed to give you one of two outcomes. If it's true, it's the outcome that's tethered to the if. If it's false, it's the outcome that's tethered to the else, exactly like in Java. And then finally, a nested if else, which is what we usually refer to as a multi-selection statement, where after each else, we can append another if to it all the way until we get to whatever the default else is. So here, if number is less than 10, we'll print number is less than 10. Else if number is greater than 10 and number is less than 20, we'll print that. Else number is greater than 20. And so let's go ahead and actually run this code just so we can see that it does exactly what we expect it to do. So what is this called? This is 10 selections. Perfect. Let's get an output of just selections. And we will compile it, and then we will run this, and we can see we're going to get the output we'd expect from the single selection, the double selection, the multi-selection. Excellent. Is there any questions related to this? It's pretty simple. Let's move on. So, as you might be aware with Java, in addition to a nested multi-selection statement, you also have the option of representing a multi-selection statement using a switch control structure. So a switch control structure enumerates, so effectively it's based off of just equality. So whereas the multi-nested selection statements have kind of the same syntax as the if and the if else, and it allows you to check for both equality and relational properties, like is this greater than or is this less than. A switch statement is only good for those instances where you're only checking for equality itself. You can't do a relational or thresholding on it. But all those instances where it makes sense, we can go ahead and use a switch format. So say, for instance, I have this number 3 here. I can create a switch construct that looks exactly the same as it does in Java, right? Where we pass in the value of our switch, and then we can define cases. And our cases are kind of like labels where we can jump from one to the other. So now when I'm talking about labels, I'm going to pull away from your Java knowledge, but I'm going to lean into your assembly knowledge, right? You would define your looping structures and your selection structures in assembly using labels and just jump to those sets or blocks of statements. And so that's effectively what a switch statement is, which is why you need to have a break to break out of it. Otherwise, you keep falling through your various blocks of code, one after the other after the other. And so Java inherits all of the behavior of switch from C. And so if I want to see this exact same implementation of this switch control structure in the form of a nested multi-selection in if else kind of formatting, you could see that right here. And effectively, they're doing the same thing, right? I have a default case for switch that could be my else that's tethered to the very end of my nested if else. And of course, it's preferable, if at all possible, to lean into nested multi-selection. That's better software engineering practices. There's some languages that don't even support switch statements. Python is one of those. Okay. And of course, if at any time you have a question, just let me know, and I'll try to, I'll take a pause and I will explain the concept more so. And of course, I can run this. Let's run this just to prove that it works, right? So let's go here, and instead of 10, let's do 11. And we can see right there, using the switch statement, the number is 3. Using the nested if else if construct, the number is 3. Just like we expected to. Okay, let's close out of that. Let's talk about loops. Pretty much done with selections. So with loops, going to look almost exactly the same as Java. Again, Java Genesis language with C, so it takes a lot of its syntax from that. So if I wanted to do a for loop, you could say I would initialize all of my loop control variables. So keep in mind that a loop has the control variable that dictates when the loop should stop. It has an evaluation on the control variable, which decides whether it should stop or not, and some kind of update to your loop control variable. So again, the defining feature of a for loop is all of the data that manages the loop itself, the loop logic itself, goes inside of the for statement, or behind the for statement inside the parentheses. So, and of course, you terminate a statement with a semicolon, just like in Java, right? I don't even know if I mentioned that because it's like saying our sentences end with periods. It's so matter of fact. Sometimes it's hard to remember that these are things that aren't necessarily true in other languages, but it is of course true in C. We also have our while loop. Again, while loops look exactly like they would in Java. And finally, we also have our do while loop, which looks exactly and behaves exactly the way you'd expect in Java. Okay, let's go ahead and just let's go ahead and compile this, make sure it runs, and then we will move on. Yep, loop basics, and let's call this loops. We need to say output, so -o for out. Let's do this. Let's remove our selections example. We don't need that anymore. And now let's run our loops example. There we go. We see using for loop, we iterate through until we hit 5 or after 5. So 1, 2, 3, 4, 5, where I is set to 1. With our while loop, we do the same kind of logic in the for loop. Effectively, for loops and while loops are conceptually the same thing, right? It's just how we go ahead and place where our loop control variable data goes. So typically, if you know ahead of time how many things you have to loop through, use a for loop, right? If you don't, use a while loop. And then the do while loop allows us to guarantee at least one execution of the loop body, even if the loop control variable would be false. So here on the last example, we had I set to 6, which is obviously greater than 5, but we still print out 6. Excellent. So let us clear our display there and let us move on here. So the next thing we should look at with loops then is going to be break and continues. And the break and continue properties are going to behave exactly as they do inside of Java. So typically we use these in loops. The break will allow us to break out of our repetition construct. So in this instance, we're going to define some variable I here. That way we have access to it after our loop breaks out. We're going to create a for loop here that would normally go until we hit the value of 11, right? Because we're going until we equal or less than 10. If I is equal to 5, we're going to print that we're going to break out, and we're going to use a break statement. And then when we do that, we're going to see it's the end of the loop. Okay, then for continue, recall continue allows the loop to continue going, but it'll ignore all of the statements that's underneath the continue. So in this instance, I'm going to have a for loop, right, where I'm going to loop until I hit I equals 11, right? So I'll go from 1 to 10. If at any time I mod 2 is equal to 0, so if on any instance that it's even, I'm going to go to continue and just skip to the next iteration of the loop. On those instances I did not trigger the continue keyword, I'm actually going to print that out. So this should only print out my odd values. And just to prove that this works, let's go here. Let's compile source code 13. Let's go ahead and run our loops application, and we can see, yes, in fact, we break out on after number 5. We stop executing on that loop. And on this instance, we're going to demonstrate continue allows us to print just the odd values. Okay, done with that, done with that. Let's clear our terminal and let's move on. Okay, perfect. Okay, so we're pretty much done with our control structures, right? That's basic control structures where we examine selection and repetition, and we talked about how we can create an atomic statement by combining multiple statements using curly braces. let's move on to something far more interesting. That's going to be our complex data structures. So we already talked about our primitive data structures, which is like our integer values, our short values, our long values, our floating point values, our double values, characters, and what have you, right? So now let's talk about how can we start creating things that look more like the objects we think about in terms of Java and arrays, right? How do we create lists? How do we create structures, structured data that can have different types of values or have the same value? One is an array, the other is a structure or struct in C. So the concept of objects and classes in Java, where Java really leans into object-orientedness, well, clearly Java inherited that from C++, which is an object-oriented version of C. C doesn't technically have objects. C is not object-oriented. So C has like the prototype of an object, the thing that existed before objects were given objects as the name, and it's what's called structures. So let's take a look at that. Here we go. Basic source code example here. Okay, let's kind of walk through this. So if I want to go ahead and create a fraction struct, I would use the keyword struct, all lowercase. You could see it in my text editor. It actually highlights. Let me see. Why is weird? Oh, one of these TVs doesn't work. That's what it is. Okay. And then I will go ahead and define what I'm going to define first. That I'm going to create a structure, a struct. Then I'm going to give it a name, such as fraction. And then inside, I'm going to create scoped variables. So here, two integers, one that is a numerator and the other is a denominator. And then I'm going to close that scope. Okay, so now let's see how we might use this in a variety of ways. I'm going to create a helper function. We're going to look at the main function in just a moment, but let's just examine this helper function. This also kind of gives us a quick preview of what it looks like to define our own functions inside of C. Again, we would have a return type. So this is going to return nothing, void. We're going to give it a name. We use the same naming principles we'd use in Java. Typically, that's what we use. So camel case notation. Print fraction. Then inside of our parentheses, we're going to have to declare the data type. So the data type is going to include both the struct keyword and what particular structure this is the parameter for. So that's a fraction. And then we give it just some identifier that we can refer to it inside of our function, right? So that's our parameter list, very similar to Java. And then this particular instance, what we're going to do is we're going to print both the numerator field and the numerator, the denominator fields of our fraction struct. And we dereference that with a dot operator, just like we would in Java. So we can access the numerator field and denominator field so that we can print it out. Okay, so now that we know what this helper function does, let's look at the main function. And the first thing we're going to do is we're going to declare some variables of data type struct fraction, and we can give them labels. We can give them a name, F1 and F2. And effectively what's happening there is that's a human readable name for us, so we can refer to it in our source code. And what's happening underneath the system is that it's going to bind our keyword, our label, our identifier to some memory address where it's going to reserve for that value. Okay, so now, like I said, C is dangerous. So we've only declared the variable. We haven't assigned any values to it, right? But we can still dereference it. It's just whatever is currently in memory will get dereferenced. Super dangerous, but I'm going to show you can do it. So what we're going to do is we're going to go ahead and print the state of the fraction before we set up any of those fields. Then we're going to go ahead and set those fields. Notice I can set those fields by using the name of the fraction, F1, F2, in this instance, just F1, and then use the dot operator to access its fields, like numerator and denominator. Again, very similar to the way we do our object-oriented coding inside of Java, right? And then we can assign those values as if they're integers. So then we'll go ahead and assign those values for the numerator and denominator, and then we'll send our fraction to this function here, which can then access those numerators and denominators to print it. Then we're going to do the same thing. We're going to take F2, right? We're going to show it what it is before we assign any values to it to show how dangerous this is. Then we're going to look at the assignment operator as it is used on structure. So you're going to see we can go ahead and copy the fields of denominator and numerator from F1 into F2. And when we do that, when we print F2, we should be able to see that it's going to have now the same denominator and numerator that F1 has. Excellent. So now that we've kind of stepped through the logic here, let's go ahead and, no, not Java. That's, there we go. Okay, let's go through and actually compile this and test it. So let's call this structs. Okay, and let's run this. And here we can see when I first look at my fractions, hey, yeah, I can access these like uninitialized values, and it's whatever random values happen to be in memory. Then we get what we'd expect after we initialize them, 22/7. We look at the random values that were in memory that is given to us at that memory address before we initialize values for our fraction 2. And then we copy the values from F1 to F2, and we see that. Perfect. And again, if you have any questions about any of these concepts, go ahead and ask in the chat or raise your hand and ask me here if you're in person. Okay, so now that we kind of see this example of a structure, that was the basics, let's look at what another preprocessor directive. So we've looked at one preprocessor directive already, which was the hashtag include. Right here. I guess this isn't a preprocessor directive. This is actually just going to be a standard keyword typedef, but we're going to look at how to use the typedef to go ahead and produce an alias for our struct fraction name. So recall on, let me go back to 14 here, because I think this is the same source code that we're going to be looking at, but there's going to be a distinction. Every time I want to refer to my structure, I have to include two pieces of data. First of all, that it's a struct. The second of all, what is the name of the struct? So that is true in my parameter list here for my functions, and it's true with my variable declarations. It's very common, therefore, in order to reduce the amount of information you need to be able to use these structs, to typedef them. Typedef them means that when you declare your struct initially, instead of just doing struct and then whatever the name is, you go ahead and you typedef in front of it. And then you can go ahead and provide a name that you want to typedef it as. So in this instance, and typically when you typedef, you use an uppercase to illustrate that this is a structure, and this is where Java starts to get its rules for object-orientedness. So this pretty much is kind of how classes are defined inside of our C programming language. So here we're going to typedef our struct fraction, and then we're going to name that fraction. And so now, whenever I go and have a parameter, instead of having to do struct fraction, and then whatever the structure name is, I can just use the word fraction, and then some identifier for it. And then whenever I need to go ahead and create a variable, I can just use fraction instead of struct fraction. And so now this is about as close as we can get to objects in pure C. And so it gives you an idea of all objects are in something like Java or C++ are these structures of data that you give some type definition to. So that's a very good question. Do they not have methods? Well, so one of the things you're going to learn about in C is we can pass. So one of the things we're going to learn about C, but not just C, but applications in general, is that everything in our system is in memory. So we usually think of data values as being things that are simply in memory. But in fact, our code that is actually executing is also in memory. And in fact, the source code that we're executing in terms of even the functions could also be referenced in memory. So there is a mechanism where you can kind of have behaviors that are tethered to your structures. And if you think about it, that's what a method is. It's like having a reference to a function that's contained inside of a struct. I'm not sure if we're going to go that deep into using C, though, as if we can pass our functions around in terms of memory. But there is mechanisms to be able to do that. And that's a really good question. But in the complex data structure, and by complex, we're talking about the primitively complex, the ones that are built into the system, we're going to think of it more as just structured data and not methods. Because methods, the idea of having a method is what brings us to that next hurdle of what objects have. Because this is effectively a structure allows you to have a collection of diverse data points, like properties, like fields, whether they're integers or things that represent Booleans. Remember, Booleans are just integer values in C, or whether it's floating point values, or whether it's effectively string or character arrays, right? All of those can be part of your structure, whereas your array, all the data types are the same. So effectively, when we talk about complex data types, that's what we're really referring to. Mixed data types versus uniform data types. And in fact, let's see here. What is no, let's see. What's the next? So we talked about typedef now. So I think that's it for our structures, at least in terms of just this overview. Let's remove our structs. And so let's close this. Let's close this. And now let's move on to our next type of complex data type, which is going to be our arrays. No. Okay, there we go. Okay, so with our array basics, you're going to notice a couple of things. First of all, it's going to look very similar to how we do this in Java. Surprise, surprise, right? So we do use box notation the same way Java uses box notation, or I should say Java uses the same box notation C does. So let's take a look at this. First, let's take a look at this helper function. It's print int array. So clearly this helper function will print the contents of our array. Does not have a return type, right? That's void. And we have two things in the parameter. One thing you should know about arrays in C, in the way they distinguish themselves from Java, is Java maintains the size of an array as one of the attributes of an array. But true arrays are just a contiguous block of memory, right? It doesn't associate any data with that. So it would be up to you as the developer to recall how much elements that array is supposed to be. You can't query the array because it doesn't know. So so that's where one thing Java has added on top of to arrays. So arrays are aware of their own length inside of Java where they are not in C. So in this instance, we're going to pass in two parameters. One will be our array. And I could have actually done this in one of two ways. I could have done it by putting the box notation after the identifier, or I could have put it here as well. Either of those should work. Okay, now with that said, I'm just going to do a simple for loop where I iterate from the 0 index to the size, and I'll print out each of those values, accessing them using box notation to read that block in memory. Okay, so with that said, let's take a look at our main function. So the first thing we're going to do here is we're going to create an array. We're going to declare an array. When we declare an array, we need to ensure it has a size because it's reserving that many blocks in memory for us to store values. So I'm going to do a int numbers, and then inside this box notation, I'm going to go ahead and put 10 to hold 10 elements. Then I will take a bad index and I'll set that because surprise, surprise, I'm going to, in the source code, illustrate how we can be very dangerous with arrays that Java prevents you from being able to do, but C doesn't care. Which is why C is so fast, by the way. It doesn't do all these checks, right? So the checks come at a cost of performance. So you can get highly optimized code if you ignore those checks. But it makes very dangerous, very bad code potentially. Okay, so let's take a look at this. The first thing we're going to do here is print the initial state of numbers before we set any values into them to illustrate, yeah, we've allocated a block of memory that we now have access to, but it's already got values because those bits are toggled in a particular way, right? So unless we initialize those values to have some state, we're just use the state that's already there. Okay, then the next thing we're going to do here is we're going to create a for loop to set each value inside of our array. Notice we can index each array element using box notation the same way you do in Java, right? And so once you have indexed into a value in an array, then you could treat it as if it's a normal variable, right? You can do assignment operations, you can do arithmetic operations, you can do whatever. And then whatever value is inside of that memory address will then get overridden with the assignment operation. Okay, then what we'll do is we'll send the value of the array to our print function. So go ahead and print the new set of values out. To illustrate that all strings are character arrays, we'll create a character array and then use a string literal, right? Where we use the double quotations to create a set of characters, and then we'll go ahead and just print that out here. And notice with character arrays, the %s is designed to go ahead and read our character by default, and we'll see this when we actually get into strings, that every string is terminated with a null character. So that's how the system knows how long a string is. So whether we explicitly put that or not, with the string literal, it's embedded for us by the C programming. Okay, so we will print that out. Then what we'll do here is we'll initialize an int array with an array literal. So remember, just like you had array literals inside of Java, we have that in C as well. So an array literal effectively uses your curly braces, and then you can have some sequence of values, and then that sequence of values will then store into this array. Since you have the sequence of values that are well defined, we don't have to declare a size then. It just uses the number of elements inside of your curly braces here. And so then we can go ahead and just send that out to print. And then finally, I told you we were going to do something dangerous. So here we're going to access index 15, print that out, because we can. Okay, let's clear this. Let's do a GCC. And let us compile this and see what happens when we run this. So -O. And let's just call this arrays. And and here we can see when we first print out our set of arrays, it's just a random set of values, right? Because we haven't initialized it, but it still has values in those memory locations. So we just look those up. Then we actually set them. So this is what we'd expect. So important lesson here, always initialize your variables before you start using them, or especially before you start reading them. Otherwise, you will get erroneous behavior inside of your C code that's very difficult to debug. Okay, this is our character array. This is how we can go ahead and have strings. So strings are not a built-in feature per se to C, right? We treat them as just collections of characters. This is with our integer array. This is with our initializer. So our literal array that uses the curly braces. And then finally, this happens to be the value that's at index 15 inside of our numbers array. We just kind of, we'll see the correlation between arrays and pointers. Probably, maybe not right now, once we get into pointers. Okay, let's see. What else do we have here? This was 16, I want to say. Yeah. Okay, so let's move on to 17. Let's close this. Let's clear my terminal. Perfect. Okay. So the next thing I want to show is our preprocessor directive of define. So in Java, typically one of the safest ways to work with arrays, since we have to declare a size of them, is not to use a number directly inside of the declaration, but to make a constant value that's readable, right? I'm sure you probably saw that in Java. And in Java, you would use the keyword const to make a read-only variable. Well, if we want a read-only variable in C, we use the preprocessor directive of #define. And then we could define some label that actually resolves to be a particular numerical value. So here, the value of 10 can be defined as array size. Whenever we have array size in our source code, when it goes to compile our code, it will replace it with the number 10. And so this allows us to effectively have a constant value so that if we have to change that, we can do it easily without having to change it everywhere in our source code. And it's read-only, it's immutable, so we don't have to worry about it consuming any memory or being overridden and change the behavior of our code. So the way that that would then look here is when I go to declare my variable, I mean my array variable, instead of using 10, I use array size. And very similar, when I go to pass a value or an array to my print int array, I can provide it the array size without having to memorize how big it is. Excellent. And I don't even think I'm going to compile this code. It doesn't even matter. It's like the same thing. It's just a good illustration. Okay, the next thing we're going to look at is going to be our multidimensional arrays. So just like in Java, where we can have arrays nested into other arrays, and the way that this is really, if you want to think about it, it's more like a list of memory addresses that can be a list of memory addresses themselves. So you can have jagged sized arrays, right? So the notation is exactly as it would be in Java. So let's say we go ahead and we do this preprocessor directive to create a size label with 10. Then let's go into our main function. I can declare a board that is 10 by 10. And so here, I kind of want to iterate through. The first thing we're going to do is, just like in Java, if you want to access something that's in a nested array or multidimensional array, you have to use the number of index values for the amount of nesting you have. So if this is a two-dimensional array, I would need a I index and a j index. Typically, you think of this as being in row column order if this is tabular, or you can think of it as outer array, inner array order. So the outer array maintains a memory address to some other array, which maintains a memory address to some actual value. And you always have to resolve to some actual value. Okay, so this is just going to set our value right inside of our board. So we'll use a double for loop, since this is a two-dimensional array. We'll index into the I, into the j, and then assign it some value that's based off of those two indexes. And so when we go to look up information inside of a multi-dimensional array, you have to understand that there's actually an efficient way to do this and an inefficient way. So by default, multi-dimensional arrays, when you're allocated memory, does it again in that row column order. So if it's a row size 10, it's going to put the first row all in a contiguous block, and then the second row will go immediately after the first row in memory, and then the next row will go immediately after that. So if you want to, so the point of efficient lookups is to minimize the amount of jumping around you have to do inside of your system in terms of where you're dereferencing from. So if it's all sequential, it's very fast and easy to go from one point to the next sequentially. It's very inefficient to jump around. So to prove this concept, and we're not really going to see the performance hit on this because it's only an array of 10, but you can see how it's going to jump around when we look this up. We're going to two different kinds of lookups. We're going to do a for loop that does our I and j, and we're going to index using ij, and then we're going to try indexing using ji. The ji is going to be the inefficient way to look up in memory. It'll actually have a performance hit related to the amount of time it takes. Let's take a look at this. Let's call this arrays. And here we go. We can see here, we have our multi-dimensional arrays. When we look it up in the order of outer array, inner array, ij, you can see we access all the individual values contiguously, 0, 1, 2, 3, all the way to 99. When we look at it using ji order, so going from the inner array and then going to the outer array for each element, you can see we're jumping around 0 to 10 to 20 to 30 to 40 to 50 to 60 to 70, 80, 90, then 1, 11, 12, 21, 31, 41, 51. So again, this is what we mean. This helps illustrate the idea of what it means to be row column versus column row. Like this is producing columns of values versus rows of values if you're looking at it sequentially. Row column is much more efficient than column row lookups in C and all C derivative languages. And the first lab, I think, will actually have you see that with arrays that are large enough to actually produce performance differences. Okay, let's see. What else do we have here? Oh, the other thing is let's combine the two concepts. We can have our structured data, so our data structures, and we can have an array of those. That's kind of like having an array of instances in Java. Let me clear this. So the way this is going to look, let's run through this source code. The first thing I'm going to do is I'm going to create a, I'm going to hashtag define an array size and set it to 1,000. I'm going to create a typedef of fraction. And so here, I like this. This is what I intended to do with the other one. I usually use the lowercase. I think on the other one, I actually used uppercase. You usually use lowercase when you define your structures. But when you typedef, you use an uppercase. So here we're going to typedef struct fraction. Then we're going to define the properties inside our fields inside of our fraction. So numerator, denominator. And then I'm going to produce a label, a definition for this type struct, which will be fraction, which we can then use as our alias throughout the rest of our source code. So here I'm going to create my function, print fraction, that's going to pass in a fraction data structure, a data struct. And then I'll be able to access its properties, its fields using the dot operator. Then I'm going to have my main function. Inside my main function, I'm going to create an array that holds fraction called numbers of size array size. So now we're starting to take all those Java concepts and you're really starting to see how it maps to C. And so then this would effectively give me 1,000 fraction structures that I have now in memory. So I can go into using box notation to access index 0 inside of my array. I can then access my properties, my fields of numerator and denominator and set those. And then I can do that at index 1. I can do that at index 2. And then I can go and send those to all get printed. So you can see I have 3 different instances of fractions in memory inside of my array for these structures. And then just to prove how dangerous this is in C, right? We don't have any of the safety nets that we've learned to appreciate in Java. We'll just go and access the element at array size, which is 1,000, and just print that out as well. So, okay, let's go here. Let's do. So this is 19. And does not like that. Okay, so that's okay. So one thing to be aware of is that there are instances where C will give you a message, a error message. So when you try to use a a literal integer, such as 1,000 or a typedef value, it will go ahead and result in this error. But let's see if we can't like break that by just doing +1 here, or +0 even, right? And now, since there's an expression there, let's see if it will let me compile. No, it won't let me compile. So let's do this. Int bad index is equal to array size +1. Save that. Clear this. And now that works. So notice there are some safety nets in there. I've intentionally tried to produce code all the way up to this point to avoid you seeing them, to show you how dangerous C is. Now you got a chance to see when there is a safety net, but how easy I can break that safety net. So I think this worked out really well. So by default, if you try to pass in an illegal value, it's going to look for that, but it doesn't get to this kind of articulation. Okay, so now let's run this. And so here you can see, yeah, that's bad, but legal. Okay. So that's it with arrays. Perfect. Let's clear this and let us remove our arrays application. Let's clear it again. Okay. Make sure there's, oh, I have a question here. Oh, I'm assuming that the question is more like an expression of horror as to how we can break code in C. Yes, that's the feeling everyone should have. A face of horror when using C. There's a reason why there's so many languages that are built on top of C. Okay, let's see here. Okay, so this is going to bring us to the next concept that's pretty important. Let me open up the source code, and then we'll motivate what it is we're looking at. And again, let me just emphasize, if at any time you want deeper explanations about some of these concepts that might not be covered in the source code examples we're looking at, you can always refer to the earlier sets of lectures from last semester where I go through the book content and PowerPoint slides. Trying to deviate it up, since you already have access to that kind of content, I think just doing very practical examples is a valuable use of our time here in class. 3 hours we get. Okay, so with that said, let's introduce pointers. So recall, one of the big things about Java, right, besides the fact that it's object-oriented, is that we can pass values around in our source code in one of 2 ways. We can either pass it by value, or we could pass it by reference. So this concept of passing by reference, the reason why Java handles referencing data in the way that it does is it hides a lot of minutia details from us. So the way that we're passing references around, what we mean by a reference is it's just a memory address of where a value resides, right, in memory. So all of memory has an address. And we'll talk much more about that in length when we get to that part of this course. And so since it's all addressable, we can access that address. We can request for some space to be granted to our application, and within that application to the state, to the values in our application. And so that will be protected so long as our application is running, so we can store values there. Then we create a variable, which is just an identifier for us in our source code, which really just maps to that memory address. Okay, so if we want to pass by reference, we have operators in C to do that, to get the memory address of where one of our variables is stored at. And that's how we can pass by reference versus passing by value. So we have to do that. We have to manage that ourselves. You're probably, so that is hidden from you in Java, but you've probably already seen this conceptually in assembly, right? Where you actually have to like jump around and manage memory addresses there as well, wouldn't you say? Or at least a concept of that. So pointers shouldn't be like so foreign to you. So you should have some example to that. So let's take a look at the source code. So right here, I'm going to create a integer variable a, and I'm going to assign to it an integer literal value of 5. Then I'm going to create a data type that is a pointer to an integer value. So a pointer is a memory address to a value where an integer is being held at. So here, and I'll just call this pointer. Now, if I want to bind something to my pointer, I give it addresses and not values. So I can get the address of this variable by using the ampersand operator. So what this line is doing is give me the memory address of where A is stored at. And so then I'm going to save that to my integer pointer, which points to a memory address, not a value, but a memory address. And just to articulate this, because that's a lot to say for 2 lines of code, we're going to go ahead and print the value of A, which should be what it claims to be, right? Whatever the integer value is. We're going to print the memory address of where A is being stored at in memory. We're going to go ahead and print the value of the pointer. And then finally, we'll show how we can dereference a memory address back into a value where we can grab the value that's held in memory using the asterisk, the star operator. So the star operator both allows us to create a variable that holds memory addresses, but if we preface it in front of a memory address, it dereferences it for us as well. So ampersand allows us to get the address of a value. Star operator allows us to get the value from a memory address. Okay, with that said, let's take a look at this. GCC 20 output. Let's call this pointers. Okay. And let's see what this looks like in practice. Okay, so we can see our value of A is 5. The memory address of where that's being stored at is this hexadecimal sequence, right? That's our addressable memory space. We can see the value of our pointer is the same thing because that's what we're saving into our pointer, the memory address of that value of A. And then you see we can go ahead and dereference the value of pointer using the star operator and get back our value of 5. Excellent. Does anyone have any questions about this? Does this kind of make sense?
Can you repeat what you mean the void on line 9 of it?
Okay, let's see here. So what we're doing here is a casting operation. Well, let's see here. Let's see if I can't avoid this by just, sometimes we have to do some things. Let's see here. Perfect. So that's a casting operation to try to make it as safe as possible where I'm casting it into a pointer value. But sometimes I like to abstract some of the things we do to protect our code for the purposes of showing how dangerous C is. So I'm glad you pointed that out. That's not something that's necessary, right? It was like a safety net. So I'm actually going to remove that. I'm going to remove as much safety net stuff as possible so that you can see what the bare essentials are that just power C. But understand there's a lot of design patterns that you usually start to build on top of this very lightweight framework, which is the language, to offer better robustness. But to answer your question, it's possible that when you start just printing out the states of memory, and if it's not referencing anything, that can create what's called a segment fault, and it can actually make your application crash. So that was there to prevent the crashing of the application if that value was not set, but it was set. So it wasn't necessary, but you got to see it because that's a safety net that we can add to our. which is now removed, so no one else will ever get to see that again. Which I think we'll get to too. I want to show some pitfalls with C, so that should be at the very tail end of today's lecture. Okay, let's keep looking at some pointer stuff, because that's kind of where I want to leave off today, is to get through all the pointer stuff. So looking at this example, we're going to look at addresses. We already talked about it, but we'll be very specific here. So we have our value of 5. We have our pointer to an integer in memory, so a memory pointer. Here, again, remember you can use your ampersand operator to get the value, to get the address of our variable value and set our pointer to that. Then we can show our original value here. Then we could show our value using the pointer. Now, the entire point of this, because up till now, this looked exactly like the last piece of source code we saw. I'm going to show you that we can actually assign values by the memory address and not just the variable name, right? So here, normally we can reassign, we can mutate the state in memory by using the assignment operator. Well, recall, this will allow us to access that value in memory and overwrite it. So now the value that will be held inside of here, inside the alias value, is modified because we changed it using our access with a pointer and not the value variable itself. So you can see how nuanced this can be by having access to memory, changing the state in memory, and what propagating effects that has to anything else that also has access to that particular memory address. And so let's take a look at this. Okay. And there we can see that this new value that's written, we're accessing that value of 10 from the value variable, but we overrode it using the pointer. But notice, in order to do that, we have to use the dereference operator to say we're treating this as the value to be overridden, not the memory address. If I tried to do this without the star operator, it would try to overwrite the memory address, which would be bad, right? That's a big, long hexadecimal value. You don't want to just put the number 5 or 10. There's lots of bad things you can do. It's going to be fun. Okay, let's take a look at some more things related to pointers. Okay, let's see how pointers relate to structures, right? Because if you think about it, a structure is a contiguous block of memory to hold different fields of values. So actually, there's a couple ways that we could potentially dereference things, and I think we'll look at that more. Let's just look at how we can use it with structures in general. Here I have a structure fraction, right, that has a numerator and a denominator. So here I'm going to create a helper function. Notice in my helper function, I don't necessarily, first of all, look inside of here. Whenever I use a star operator alongside the data type, that's saying this is expecting a pointer and not the actual value to be passed in. So it's a pointer to, even though a data structure is a memory location in itself, you could have a pointer to that memory structure. So this is expecting a pointer to a fraction, not a fraction. So I can then access elements from a pointer of a struct using the arrow operator. So from the memory address of a fraction, I will access the numerator and the denominator. Okay, so now that we've kind of defined what's going on inside of this function, let's look at the main function. So here I'm going to create an actual fraction value. Notice how I'm actually doing this. We're actually going to use a, since both numerator and denominator are integer values, I can actually create a literal array value. and bind that to my fraction, because that's effectively what a fraction is, 2 integer values. So here, this will allow me to set my numerator and denominator. So that's what I'm doing here. Then I'm going to go ahead and use the ampersand operator to get the memory address, the address of where that fraction is in memory. And I'm going to bind that to my fraction pointer. So this now points to my fraction in memory. Then I'm going to send that pointer, F1. So I'm going to send that pointer to my print fraction, which is looking for a pointer to a fraction. Then I'm going to use the arrow operator to access its fields so I can print it out. And we can see if I go and run this, exactly what it looks like. And there you can see it does exactly what you'd expect it to do.
You got a question?
Oh, excellent. Okay, so some questions. Clearly, we have a statement: with great freedom comes great responsibility. This is true. So it's up to you to make good C code. And then we have a question about the pointer. If I rewrote the address on it, it rewrites the address off pointer, but the memory structure it was pointing to before remains, right? So, okay, let me think about this. If I'm understanding the question correctly, there's 2 levels of indirection that are happening when we create our initial structure. So the structure itself is not a primitive value, right? So it's a value that's being stored in memory. So when I create this fraction here, it's kind of creating a memory address block that's going to hold my denominator value and my numerator value and my denominator value in that order. Then when I create this address, I'm going to grab this address towards that fraction, and that's going to be a pointer to that same fraction object, effectively, or the address of where that fraction object is at. Now, if I use the pointer to change the values, it will change the values to my fraction. But one is the memory address to my fraction. The other is the memory address to the 2 contiguous blocks of values, which is the numerator and denominator. And sometimes those might be the same thing. And if you ever want to check, just print out the memory address of the fraction and your pointer and see if it's the same. So I'll leave it up to the class to actually investigate that. Okay. Let's take a look at dereferencing again, just because there's 2 different modes of dereferencing we've talked about. So let's again look at our structure. We're going to typedef it as point. So now I'm going to create a function that's called that takes in a point. And notice this isn't a pointer to a point. Kind of regret calling it point. And I can dereference those values with the dot operator when it's the actual point. Whereas when it's a pointer to the point, I would use my arrow operators. So here you can kind of see in our source code how we talked about this both times. And notice here, when we're passing our pointer to the point, so let's actually step through this. Here, I'm going to create a P1 point using the values of 10 and 20. Here, I'll get the address of that point, and I will save that into a pointer variable to a point. Then I'm going to dereference that address into the actual point, because that's what needs to get passed into my helper function. But I can also use my pointer to access my X and Y using the arrow operations, provided it's a memory address, or the dot operator if it is the actual point structure itself. I'm not even going to bother compiling this, right? This I think is more of a visual thing. You can kind of, I'll do it. I mean, the behavior is going to be what you expect it to be, right? But we will do it anyway. Here we can see my point dereferencing using my star symbol. and using my arrow notation. And what's not illustrated here is that we're also using the dot notation when we do the print statement. Okay, let's see here. We are on 24 now. These little bite-sized code examples are easy to get through very quickly because they're hyper-focused on a concept at a time. Okay, so here I want to illustrate just like you can have multi-dimensional arrays. And if you think about it, arrays are just ways of dealing with contiguous blocks of memory. We can have pointers that point to other pointers, right? So we can have just pointers that point to other addresses. That's what that means. A memory address to some other memory address that resolves to some other value eventually. So you can think of pointers to pointers as being conceptually similar to multi-dimensional arrays. So in terms of the way that we can use them. So let's see what that looks like in practice. Here, I'm going to have an integer value 5. I'm going to grab the address, the memory address, and I'm going to put that to a pointer. Now that pointer itself is a variable, which means I can use the ampersand operator to get its memory address, because the memory address is stored in memory, which means we can access it and save that to another pointer. But we have to say what data type that is. It's not an integer, it's a pointer type. So, and it's a pointer type to a particular type of data, because when the reason why the type of data is important is each type of data, it takes X amount of bits, a certain number of bits to go ahead and encode. So it knows how many bits are stored for that particular value. So for instance, if it's an int value, it's going to be 4 bytes worth of bits versus a double value, which would be 8 bytes of bits. So it allows the system to know, how, starting from this position, how many bits of a sequence do I need to encode or save to hold a particular value of that data type. So this is going to be a pointer to an int. And let's just see what that looks like in practice. Let's clear this. Let us and we will run that, and you can see my value is 5, the value via the pointer is 5, the value via the pointer to the pointer is 5. Okay. Let's take a look at what it looks like for our pointers for arrays, because there's a lot of synergy between these two. And we're going to talk more about this in the upcoming class as well. So here, let's say I have my a structure here, numerator, denominator. Here, I'm going to go ahead and use a pointer to my fraction. Here, I'm going to create my fraction. And notice I can have a pointer right into my array at index 1 by grabbing the address of F1 here and then send that out to get printed. And we'll look at a deeper example of this next class. I kind of want to see if I can't get through these last couple of examples. So the idea of a pointer that doesn't have any memory address is the value of 0. So a pointer that's set to 0, since it's an integer, since it's effectively a unsigned number that represents a pointer, then we have a value that's called null that defaults to 0. It's equal to 0 to represent a null pointer. So here we'll create a pointer. We'll assign it to null, and we're going to check equality, our pointer to null. We're also going to check it to 0, and we're going to say it's the same. So a null pointer just means there's no point in the memory address. It's not pointing to any place in memory address. So if you're wondering where that comes from in Java, this is exactly where. And here we could see, oh, clear that. This is actually 26 that I want to do. I want to spend a lot more time talking about arrays and pointers in particular. So we will skip that other one and let's run this. And we can say, yep, So our value of the pointer when it's null is 0. So if we check using the equality operator with null, if we check with the pointer to 0, it's going to be the same. Okay, give me a few moments just to go through these last two because I want to talk about something else. Actually, I also have a message to send about next lecture as well. So the last couple of things I want to illustrate now that we've introduced what a null pointer is if you want to create more complex entities that can self-reference themselves, like a linked list, this is a simple example of that. I can create a structure node that has some value, payload, like an integer value, and it can also have a value to a struct, an address to a struct to another node. So in order to reference another node, you have a memory address in memory that would represent that different node. So when we go into our main function, we can go ahead and have our node 1 and our node 2. And so suppose that we are going to set our value to data, and then the default memory address is just null, no pointer anywhere. Then suppose for the property of next on node 1, I can then give it the memory address to node 2. So now node 1 has an address to node 2. Then if I go and print my list, giving it the memory address to node 1, and let's jump to this print list, it's expecting a pointer to a node. So here I will create count. So while my node is not null, because that's a pointer, I will print the node and then grab the data from it. And then I will overwrite n, which is the memory address, with whatever memory address is inside its node, its next property, which is a node memory address. And so that should move us to node 2, but node 2 is going to be null, so we should stop. Let's actually see what it looks like to build a very simple linked list using C, so you can map this more precisely to your Java knowledge. And so here we can see when we run this, we would get node 1, which has a value of 100, and then node 2, which has a value of 200, and then we stop. So the last piece of source code I want to show, so that it all gets included in the same video, is the pitfalls. Clearly, there's lots of dangerous things we can do. I want to show you what happens if we try to access a memory address that we did not initialize. I think that's one of the most dangerous things you can do with pointers, and it's definitely worth mentioning when we're introducing the concept of pointers. So here, we are going to have some source code where I'm going to create a pointer to an integer. I'm going to do some sets of values on arrays, some kind of operation. So we're mutating the space of memory. Then I'm going to try to assign a value to our pointer to dereference to our pointer, right? We're dereferencing, but we never assigned it. So this is some random value. And so what this is probably going to do is it's going to crash our system. So what this means is whenever you use a pointer, you want to make sure you initialize it. And let's run this. Yeah, I get a segmentation fault 11. So this is what happens when I try to point in a location in memory that I don't actually have access to. That's outside of the bounds that the OS has provisioned for me. And that's because I've created a pointer variable, but never actually assigned it. If I want this to work as per expected, let's comment this code out. And so when I create my pointer here for P, I actually should assign it some address to a value that does exist. So it actually has a memory address that's within inside the bounds of our application. And then I can do this action of dereferencing it to assign a value, and that would be legal. So let's do this one more time just to prove that this will run if we comment that code out. And yeah, you can see the correct usage value 13. Okay, that should be a good introduction from everything from our control structures to our pointers. Now, I have to make a big announcement that on Wednesday, I actually have jury duty. So I won't be able to attend class live. So it's my intent to make a pre-recorded lecture that I expect everyone to watch during our class time while I'm sitting inside of a room waiting to get called. And I'll pick up our Monday lecture where I left off on the video. So I will trust all of you to watch that. Otherwise, you will have a hole in your knowledge.